Hello, my name is Sertaç, and this is my engineering graduation thesis and Istanbul Aral University, supervised by Haluk Gümüşkaya. My project is called Detection of Vehicle Violation Hedge Areas using Computer Vision Istanbul Traffic. The goal of this project is to detect vehicle that miss hedged strip no drive areas is traffic. In Istanbul, some drives use these areas to bypass the queue and merge back ahead of other vehicles. In Turkish, this is behavior is commonly called kaynak yapmak. I built is a computer vision pipeline that detects vehicle that them over time confirms real violation and creates reviewable evidence. The system is designed and offline prototype, but the idea is practical if the camera footage already exists. The software can help an operator find suspicious event much faster than manually watching. Uh, School. Hedged hedge road areas are designed to keep traffic organized and safer, but in dense traffic, drivers sometimes enter these zones, drive along the stripes, and cut back into the line. This is unfair for other drivers, increase accident risk, and makes congestion worse. Manual enforcement is also difficult because an officer cannot continuously watch every camera feed. So, the main question is, can an ordinary traffic camera automatically detect only the vehicle that rarely violate the hedged area without creating too many false alarms? This is not only an object detect problem. Detecting a vehicle is one frame is not enough. The system must understand the vehicle movement over time. For example, a vehicle can legally move near the hedged area or briefly touch the boundary during a normal lane change. If the system rigged to only one frame, it will create many false alarms. That is why this project focuses on behavior over time. The project has six main objects. First, detect vehicles in Istanbul traffic footage, cars, trucks, uh, bus, and motorcycles. Uh, Second, track each vehicle across frame. Uh, so the same vehicle keep a stable identity. Third, uh, confirm violation violation using temporal logic, not a single frame decision. Fourth, classify the violation the type and calculate a severity score from the 0 100. Fifth, project privacy phase and not process and license plates and read only after violation is confirmed. Finally, provide a usable Gradia web application where the operator can upload the a video, draw the hedge zone, run detection, and review the evidence. The scope fix camera footage, especially roads where the hedged zone is visible from the overpass or similar viewpoint. Real-time deployment, automatic camera calibration, and full city-scale integration are not part of prototype, but they are possible feature extension. Uh, for vehicle detection and violation analysis, I created my own dataset called the Istanbul Hedge Area Traffic Dataset. I collected real Istanbul traffic footage from overpass waypoints and different road location where hedged are visible. This was important because generic public traffic dataset do not fully represent Istanbul traffic. Local road layouts or traffic-specific quasi-jumping behavior. The dataset contains uh, for after export output in the dataset covers for vehicle, truck, bus, motorcycle. It was hand labeled and split into training, validation, and test sets. In testing, our dry labeling, the goal was not only to train a general vehicle detector, but to make the detector reliable in the exact visual contents of this project. Dense QAs, particularly o- occluded vehicles, perspective from above, and vehicle close the hedged zone boundary. For license plate detection, I use a separate Turkish plate downloaded from RoboFlow. I trained a plate detect and that dataset, and the plate detection model reacted 0.98 map 50. In the final system, this plate model is used only for confirmed violator, not every vehicle. So there are two different data parts of in project, my own Istanbul dataset for vehicle and violation and analysis, and the RoboFlow Turkish dataset for the plate detection component. Let's go another slide. The system has four main steps. First, the video frame is taken from the traffic footage. Second, a YOLO V8 model detects the vehicle. Uh, Third, by the track follows each vehicle and as assigned in track ID. Fourth, the system check each vehicle trajectory against the hedge zone polygon. The most important is the temporal violation state machine. A simple system might mark a violation as soon as vehicle touches the hedged area, but these cause false positives. A vehicle can touch boundary for a moment during a normal lane change, or the detector can have a small box error. My system waits and watches the vehicle over the system frames. The vehicle moves toward states as outside, entering inside, and violation. Only when behavior is consistent enough does the system confirms a real violation. After that, the system saves the violation type, severity score, timestamps, vehicle ID, and evidence snapshot. The severity score is useful because not every violation has same important. A vehicle that only touched the edge is different from a vehicle that drives along the hedged zone, skip the queue. By assigning a score, the system can help the review focus on the strongest cases first. The system also separates different violation styles, such as the crossing toward and hedged area. edge connect and lane change toward the area. This makes output uh, more information than simple yes or no violation label. Uh, the project is implement Python. Uh, YOLO V6 YOLO V8 is used for vehicle detection. Track is used for multi-object tracking, Shapely and Polygon, Geometry Hedge Zone, Easy OCR, Paddle OCR is used the plate reading part. SQLite, provides web interface. Uh, let's go. In the demo, the operator first uploads a traffic video, then hatched area is defined by driving a polygon on the first frame. This is currently manual because every camera angel sees the road from a different perspective. After setting the tree salt, the operator start the pipeline. The system detect vehicles, track them, check their movement against the zone, and marks confirmed violation. Uh, the output is sorry. The output is enacted video and a violation log. They include the time steps, vehicle type, violation type, a severity type, and evidence snapshot. This is important because the result is not only a visual alert, it is a record and the reviewable later. In the enacted output, a normal tracked vehicle are shown separately from confirmed violators. This makes it easier to see that the system is not simply flagging every vehicle near the zone. It is using the tracking history and state machine result before predicting an alert. Uh, mm, yes. Result, the vehicle detector reacted 0.899 8096 on the rest set. Cars, truck, and bus are detected strongly. Motorcycles are more difficult because they are smaller, less uh, particularly occluded. Uh, in this gives yes in the particle in the for the full pipeline field test, I evaluated the system on real Istanbul footage. Uh, yes. Yes. For the full field test, I evaluated the system on real Istanbul traffic footage. There are 10 real violation in the tested video window. The system predicted uh, 9 alerts out these. 8 were true proofs, positives. I was a false positive, and 2 real violation are missed. Uh, The false positive show that the problem is still challenging, especially when vehicles are close together when the boundary interdicting ambiguous. The missed violation show that recall and can still improve with data, better tracking stability, and more deforce uh, test clipping. Uh, the main contributors are a custom Istanbul traffic dataset, YOLO A V8 vehicle detector adapted a local traffic, temporal state machine for reliable violation confirmation, severity scoring, privacy-aware plate recognition, and a working radio web. There are also a limitation. The system is not yet optimized for real-time citywide deployment. Motorcycle and distant vehicle are harder. More data is needed, rain, fog, night condition, and more diverse camera angles. The edged zone is also drawn manually for now. Future work would include explaining the dataset, improving motorcycle and night performance, automatically detecting hedge zone and optimizing the system for CPU or edge device deployment. Overall, the project combines and model training, tracking, geometric reasoning, temporal decision logic, privacy-aware plate handling, and working user interface into one complaint pipeline. Thank you. Uh, yes. To To include this project show that ordinary traffic camera footage can be used to detect hedge area violation is more reliable and reviewable way.